Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Want to get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
very much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. So later for my college, I get to know about XLR and I enrolled in XLR course. It was really good experience. Our course has been taken by Mayur sir, and he was very good teacher. He not only focusing on theory part, he is doing how real digital marketing works, and it was in total very good experience. I get so much of knowledge. Here they're not only focusing on study, they're also conducting different exam to test our knowledge. And as we are giving the exam, so to appreciate our work, they give certificates for the toppers, and along with the certificate they give hampers. Thank you, XLR.
Recently, I was searching for digital marketing courses online in Google, and I came across XLR, and I attended a digital marketing course which was for 15 days. My mentor Mayur helped me for attending these classes. So he is a very informative and helpful guy. In the course end, there is a exam which I topped, so I came to the XLR office in Bengaluru. This digital marketing course has helped my career and my skills to develop. And
good evening all. Students, kindly inform your friends to join the session. As I can see today, participants are very less. Please, I request inform your friends to join the session. So we are starting the session for the day today. Alil sir, good evening.
Yeah, good evening.
Yeah, you can start the session, sir.
Okay, no problem. Down on sir. Okay, good evening, everyone. Am I audible?
Yes, sir, you're audible.
Okay, fine. Hope my screen is visible to you all.
Yes, it is visible.
Okay, fine. Thank you for confirmation. Yeah. May I know what we discussed yesterday? Just a quick recap within 2-3 minutes. I guess my screen is visible to you, and all the sorting techniques that we discussed till now that are shown over here. Right? These are the sorting techniques that we discussed. Right? We have bubble sort, we have selection sort, insertion sort, merge sort, and quick sort. And then we comparatively study all these sorting techniques. What's their complexity, best case, worst case, average case, and so on. So I guess we discussed it, right? Yeah. Okay, this was, it is showing more details as compared to the previous slide. If we see, now you have to, I can't say remember the things, you have to like now logically think about it. only selection sort is having the complexity of order of n square in all the three cases. When we take these three into consideration, right? Bubble sort and selection sort, I discussed it in detail. It is having only order of n when the list is already sorted. So you don't have to like compare again and again. Similarly, in the insertion sort. But in selection sort, once you select an index, once you select an item, you have to compare that with the sorted list as well. That's why it is best case complexity is also n square. Then we discussed these three yesterday, these two rather, merge sort and quick sort. And both are making use of divide and conquer. So they will involve log n, right? So they will involve log n, and this n is for the work done. Means in merge sort, when we merge the list back, right? So it will be making use of this n work done. That is why it is n log n, n log n, and n log n. But in quick sort, see, we are checking the worst case as of the order of n square, and I have explained it. Whenever you have a sort this list, and whenever you choose a pivot at the front or at the back, at the last of the list, right? So it means when this is smallest or this is biggest, at that time when we divide the list, the one list remains empty and another list contains n minus 1. Similarly, at second level, same thing happens, and so on. So it is making a kind of a linked list, right? That is why it is complexity turns out to be order of n square in case of this quick sort, right? And remember these complexities as well. So these are the things that we discussed till yesterday. If you have any questions or you have got any doubts, you can ask, or you could have asked me yesterday itself. If not yesterday, you can ask me right now. Okay, fine. Now let us go to the next topic, that is recursion. Yeah, what is now recursion? Can anyone? What is recursion? Whatever you know about the recursion, just type your definitions or whatever you have in your mind regarding the recursion. Okay, function calls itself, good. Repetitive process, nice. Great, again and again. Fine. Good to see your answers. Great. Okay. We can simply say this recursion is a programming concept, right? Where a function calls itself, as you already write it in your chat box, that where a function calls itself, and it is like whenever we have to solve a problem, and this recursion is a programming concept where a function calls itself to solve smaller versions of the same problem, right? You can think, if I will give a layman's example of recursion, you can think of peeling an onion, right? You are peeling an onion. So we know that this onion has got so many layers. Whenever we peel one layer, it reveals another similar layer underneath it. Then we peel that layer also, another similar layer is revealed beneath that, till we reach the core of the onion. It is like recursion, means it is recalling itself. One layer peeled, underneath it is a similar layer. That layer peeled, underneath that is a similar layer. It means that we are peeling this onion until we reach to the core of the onion, right? Or we can take another example, like you might have heard about the Russian doll. right? So we have got a doll. Inside a bigger doll, we have a smaller Russian doll. Inside that, we have another even smaller one. Inside that, we have another smaller one. And eventually, when we go deep, 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 we reach to a smallest doll inside the core. So that is like recursion. Each layer calls the next until we reach the smallest unit. Like in onion, we reach to the core. And like in this rice and doll problem, we reach to the smallest one among all the dolls. So when we reach the smallest one or the core of the onion or the smaller version of a bigger problem, we call that as a base case, right? Okay, so we call that as a base case, right? I hope you got it. Yes or no? So it is simply a programming technique where a method calls itself to solve a problem by breaking it down into smaller problems. And these smaller problems are similar sub-problems, right? Like in case of onion, as I already told you, when we peel a layer, beneath that is the similar layer. When we peel that layer as well, beneath that layer is one more similar layer. Similarly, underneath that is one more similar layer until we reach to the core of the onion. And that core we call as a base case. Similarly, in case of rice and doll problem, we have a doll. Inside that, we have a smaller one, smaller doll again. Inside that smaller doll, we have another a bit smaller one. So until we reach the smallest of the all dolls, that is inside the core, and that is called as the base case. So this recursion actually consists of two parts. One is base case, the condition that stops the recursion. Means in case of the onion, it is the core. At that time we stop. We don't further peel it because it is not further peelable. Similarly, in case of a rice and doll, the smallest one that is inside the core. Inside that there is nothing. That is the base case. Right? So base case is the condition where the recursion stops. Means the condition that stops the recursion. That is the base case. And another thing is the recursive case. Recursive case is simply the method that calls itself with a modified input to progress towards the base case. It is simply a method which calls itself in order to reach the base case. Means we are solving the problem by recursively calling a method, right? The method is similar to the method which has called the previous function. It is like peeling the onion. It is a kind of a method. Means how do you peel it? That is a method. You have peeled the outer layer. Again, you are going to peel it. The method is same. You are peeling it. The third method is same. You are peeling it till the method will work till what? Till you reach the base case. So when base case is reached, condition fulfilled, recursion stops. So this is how actually recursion works. Right? Is it clear? Is it clear? Okay, now why do we use recursion? Can anyone tell me why do we use recursion? It's simple. Whenever we are incorporating any kind of a method or a process or any like that design strategy, the ultimate aim is to solve the complex problem. Because whenever you have got any kind of a complex problem and you want to solve that complex problem, you have to devise a method. So this recursion is also used to make the complex problem simpler to solve. Means with the help of this recursion, we can solve the complex problem, or I can say it makes the complex problem simpler to solve. And may I know where this recursion is most oftenly used? Can anyone? See, when we go to the mathematics, simple, where it is used. Most famous problem is in algorithms, mathematics, where we make use of recursion. Can anyone name? Yes. Yeah, great. Factorial is there. Fibonacci numbers are there. So those problems are solved with the help of this recursion. And in data structures, where we make use of recursion. Yes. In data structures, where we use recursion. Which data structures are making use of recursion? Okay, it is tree, it is graph, it is like stack. So these are the data structures that are making use of recursion in order to solve the complex problems. And in backtracking also, like for example, when we are solving the Sudoku problem or maze solving problem, for those problems also we are making use of recursion, right? So these are some of the problems where we are making use of this recursion, right? Okay, as I already told, it has two parts. One is base case and another one is the recursive case or recursive call. On the base of these two things, the recursion is working. Hope it is clear. Yes. Now, there is a problem, mathematical problem, or it is also an algorithmic problem. Means whenever we are calculating the factorial of a number, and we all know what factorial is, right? There is no need to like define the factorial. Simply it is, if I have to write the n factorial, it is equivalent to n into n minus 1. I can write factorial, or you can write n into n minus 1 into n minus 2 till you reach the base case, means the 1 factorial. It is equally likely. Keep this onion peeling or the doll concept in mind. So with this now, when you like I can say make an analogy of that, the things will become clear. Like here, see, I am computing n factorial, isn't it? So n factorial is equivalent to n into n minus 1 into n minus 2 into n minus 1 into 1 factorial. Right? So I have to reach to some point where this recursion actually stops. And we know where this recursion actually stops, that is the base case. So here the base case is what? Here the base case is 1, means 1 factorial is equivalent to 1. Right? So for the remaining, I have to compute all these things. If we go to the like I can say write simply a Java program for it. See, let us explain it. This program. Simply, firstly, I am simply making a class of factorial. You know, class is the blueprint. No need to explain it again and again. Then I will be making a recursive method to calculate factorial. So I will create a method in order to calculate this factorial of a number, right? So for that purpose, what I will do, I will create a function. We call that as a factorial, right? Then I will pass some number, like suppose I can write, let it be 6 factorial. Now see, it is, consider this as the outer layer of the onion, 6 layer. In order to compute 6 factorial, what we have to do? We have to peel it off. When I peel it off, there is the 6 outer layer that I peeled. Inside comes 5 factorial, right? So I want to peel that off as well, because I don't know what is inside. So I peel off the 5 factorial here. When I peel off the 5 factorial here, it is 6 into 5. Then I go to 4 factorial. I peel that off as well. 6 into 5 into 4 factorial. For 4 factorial, peel it off. It becomes 6 into 5 into 4 into, now the third inside part of the onion, it is 3 factorial. I peel off the third layer, means 3 factorial here. It is 6 into 5 into 4 into 3. Then it comes 2 factorial. So it is 6, 5, 3 into 2 into 1 factorial. When I reach to the 1 factorial, it is the core. It is the base case. So when I reach this 1 factorial base case, it means 1. So when I like calculate, it is 6 into 5 into 4 into 3 into 2 into 1 factorial. 1 factorial is there. Base case, it is 1. So I am just computing the 6 factorial. It is simple. Right? So for that purpose, what I am doing, I am simply checking some conditions. If n is equal to 0 or n is equal to 1, this is the or, two pipes. We write these two pipes in programming, this and this. This means or, and you might be knowing it well. So this is the base case. Means if n is equal to 0, because what is 0 factorial? What is 0 factorial equal to? May I know? What is 0 factorial equal to? Okay, 0 factorial is equal to 0. Yes. 0 factorial is simply defined as 1. Okay, yeah. 0 factorial is equal to 1. Great. Because it represents actually the possible arrangement of some empty set. Okay, let it be. So we are at the base case, means when n is equal to 0 factorial or n is equal to 1, means 1 factorial is also equal to what? It is also equal to 1. So that is the base case. Means the core of the recursive problem. Right? Then return 1. Simple. Else we have to make a recursive call. Means we have to peel it off. We have to solve the problem. We have to go to the core of all the dolls. We have to check how many dolls are there inside the bigger doll, then another doll, then another doll, and so on. So we have to solve that. We have to go to this base case recursively. So for that, what I will do, I will simply return n into n minus 1 factorial. Means I have created a factorial function. So it would be simply n into n minus 1 factorial. Right? When I will go it will recursively call what? N minus, if it is like n factorial. This will call what? This will simply, okay, here it is. Let me remain on this slide itself. Then it would be it is not moving here and there. Okay. Then it would be n minus 1 factorial. What it would be equal to? It would be n minus 1 into what? N minus 2 factorial. Then n minus 2 factorial will be in turn equal to n minus 2 into n minus 3 factorial, and we will go till how much? Like 2 factorial is equivalent to 2 into 1 factorial, and we know 1 factorial is equivalent to 1. So this is the base case. So this is how actually it is working, right? So this way we are calling the recursive functions. If we go to the next slide as well, here I have shown the problem. See here. Let me clear the drawings again. I am computing Fibonacci of 4. So Fibonacci of 4 is simply, no, it is a tree actually. In order to compute the Fibonacci of 4, I have to compute, let me take not Fibonacci, I will check the factorial problem. Okay, let us discuss first factorial. So for example, same case, I will take the case of 5 factorial recursively. So 5 factorial, for 5 factorial what I have to do? 5 into 4 factorial. For 4 factorial what I have to do? 4 into 3 factorial. Then for 3 factorial, I have to write 3 into 2 factorial. For 2 factorial, I have to write 2 into 1 factorial, and 1 factorial is equivalent to what? 1. So when I recursively combine them, it would be 5 into 4 into 3 into 2 into 1. So it would be equivalent to what? 5 4 the 20, 60, 120. So this is how it actually works. Fine. Is it clear? Then we'll take the case of Fibonacci series. Is it clear? Do you have any doubts how it is working? Is it fine? You want me to repeat it or it is clear? Okay. Let us take the case of Fibonacci series now. Second example, this. Yes, this was factorial breakdown that I discussed. Factorial of 5 we return 5 into 4 factorial, 4 into factorial of 3, 3 into factorial of 2, 2 into factorial of 1. I guess I discussed it. Then 1, it is the base case when n is equal to 0. So it will simply write factorial of 0 is 1, factorial of 1 is 1 into 1, 2 into 1, 3 into 2, this into this and this into this. Actually, if we go deep into the detail now, it is making use of stack. Let me explain it a bit. I don't know whether you will be able to carry it or not. 1 2 3 4. See, this is the problem. 5 factorial, right? So whenever this 5 factorial comes, it goes to the top of the stack. Means push operation happens. Right? We call it as push 5. So it will go here. Then see here, 8 return is 5 and factorial of 4. So when it tries to compute the 5 factorial, it comes up with another recursive call. Means it peels off the another layer. That is 4 factorial. Right? Then it tries to find another. Means another push till another push. Then 1 factorial. And we know when we go to 1 factorial, it is a base case. It is equivalent to 1. So when it reaches 1, means no more this factorial function needed. It starts to pop. So it will do what? It will do the pop operation. So whenever it will do pop, it will try to write 1. Fine. So now what will you do? It will pop 2 factorial. So it will 2 factorial. We know it is simply 2 into 1 factorial, and we know 1. So it is 1 into 2. So it will start popping. Again 2 factorial pop, then it will start popping 3 factorial. So here it remains 1 into 2 factorial into 3 factorial. So that is 3 into 2. Similarly, another element popping. So it would be 4 and it would be finally 5. So with this, stack remains empty because all the elements are popped up and recursion stops. So the element that is returned is 120 is the result. So this is how this stack is used for the recursive operation. Hope it is clear. Stack operation we call it as. How stack is used in recursion? Remember it. Which of the following data structures is used for recursion? At that time you have to write stack, and I have shown you how stack is used. Okay, just a thumbs up if you got it. If not, I will repeat. Hope it is clear. Okay, let me repeat. Let me clear the drawings. What is this? This is stack, right? Isn't it? So this is stack and this is TOS. TOS means top of the stack. And what do we want? We want this to compute 5 factorial. Factorial of 5. Means it is a function. So whenever 5 factorial comes, it goes to the top of the stack and push operation happens. So we'll be pushing, PUSH, push operation happens. So by push we mean 5 factorial will be inserted to the top of the stack. So there is nothing in the stack, so it would be 5 factorial. So let it be, it will go to like suppose top of the stack. And now it tries to compute 5 factorial, but there is a factorial function. So in order to compute a factorial function, it has to peel off all the layers until it reaches the base case. So in order to reach the base case, it has to compute 4 factorial. So it now there is 4 factorial because it returns 5 into factorial of 4. When it reaches the 4 factorial, that also goes to the stack, right? So it tries to compute 4, but when it computes it by the definition of this recursive function, n into n minus 1 factorial, it finds out that it is 4 into 3 factorial. So when 3 factorial comes, that also goes into the stack. So now it tries to compute 3 into 2 factorial comes there. So that also goes to the stack. Now when it tries to compute 2 factorial, it is 2 into 1 factorial. And we know 1 factorial is what? It is equivalent to, because there is no more recursive function, it is the base case. Or I can say 1 into 1 or 0 factorial, that depends. So I am simply representing the base case as 1 factorial is equivalent to 1 because I have to designate this base case. So I am writing 1 into 1 is equal to, when I write 1 into 1 is equal to base case, there is no recursive call because it reached the base case. No more function, recursive function, no more factorial there. So it will start popping. So it will pop, right? So when it will pop, it is 1, right? Then after checking, it will try to find the another pop element. So it will multiply them, n into n minus 1 into n minus 3, 2. So it will start computing 1 into 1. Then when 2 gets popped, it is 2 into 1. When this element gets popped, it is 3 into 2 into 1. When this element gets popped, it is 4 into 3 into 2. When this element gets popped, it is 5 into 4 into 3 into 2 into 1. That is 120. So with this, stack gets empty and we are returning this factorial value. So this is how stack is used for recursion. I hope now it is clear. Yes. Just a thumbs up if it is fine. If not, do let me know. Yes. Clear? Great. Okay, now let us do another example of Fibonacci series. Let me clear the drawings. It is also simple. See, as I already told you, always remember two parts of this recursion. One is base case, another one is recursive call. So first of all, we usually designate the base case. Here the base case is if n is less than or equal to 1, return n. Simple. If n is less than or equal to 1, return n. Else, recursively call the function Fibonacci of n minus 1 plus n minus 2. It is simple. If you remember the Fibonacci series, it is 0. What is the Fibonacci series? It is 0, 1, 1, 2, 3, 5, 8, 13, then 21 and so on. So this is the Fibonacci series. Means any element in this Fibonacci series is the sum of previous two elements. Means if I have a function f of n, recursive function, we discussed it previously, it is f of n minus 1 plus f of n minus 2. So this was the recursive function, right? And when we iteratively solve it, we usually write f0 is equivalent to 0 and f1 is equal to 1. In most of the programs, you are writing like this, isn't it? Then we compute the Fibonacci series. Here also, if we check n less than 1, it is base case, return n, whatever is the n. Means if n is equivalent to 0, return 0. If n is equal to 1, return 1. So first two elements are 0 and 1. If n is greater than 0, this 1 means if n is 2, 3, 4, 5, then compute this. Means we have to compute this. Na? Or I can say we have to compute the function that I have written over here. So this is the value that we have to compute when n is greater than 0 and 1, means these two values. So the base case is simply f0. While we were discussing dynamic programming, the concept of memorization. I don't know whether I have written that over. Yes, Navi recursive Fibonacci. Yes, I have actually written it in the presentation. So we'll be discussing it. Why it is inefficient and why this other one is efficient. Okay, now let us first explain the problem, then we'll go into the detail of it. See here, we are actually computing Fibonacci of 4. So whenever we compute Fibonacci of 4, we require Fibonacci of 3 and Fibonacci of 2, isn't it? Because I have already told you it is sum of previous two terms. Fn minus 1 plus Fn minus 2. So this is the that we have to compute. So it is simply when I write Fibonacci of 4, simply I will write now 4. It is 3 plus 2, right? And this 3 is in turn equal to what? Fibonacci of 2 and Fibonacci of 1. Similarly, here Fibonacci of 2 is equal. Remember it, how I am doing and how I am doing it. Then 2 is equivalent to simply Fibonacci of 1 and Fibonacci of 0. Simply. So after that, as we can see, there are many calls repeating. Like suppose here it is repeating, here it is repeating. So this Fibonacci of 2 is calculated multiple times, right? Remember it till now. Okay, so it is calculated multiple times. When it is calculated multiple times, we call it as Navi recursive Fibonacci or Navi recursion. See, here also you have to compute it. Here also you have to compute it. So if you have to compute now, like suppose I will tell you compute 8 factorial like this. Fibonacci of 8, not 8 factorial, Fibonacci of 8. It would be equivalent to 7th term plus 6th term. 7th would be equivalent to 6th plus 5th. Simply 6 would be equivalent to 5th plus 4th, isn't it? Then again this 6th would be equivalent to 5th plus 4th. Then 5th would be equivalent to 4 plus 3rd. Then this 5th also would be equivalent to 4 plus 3rd, isn't it? This 4 would be equivalent to 3rd plus 2nd. So with this way we are like calculating this Fibonacci na, and there are so many repetitive columns. If we check here 6, here also, then 5, here, then 4 is so many times. Similarly 3 is so many times, and 2. So it means it is containing so many repetitive calls, right? Or in other words, we can say there are many calls that repeat, like 4, 5, 2, 3, etc., etc. Means 4 factorial is calculated multiple times. Similarly, 3 factorial, 2 factorial, 5 factorial, and even 7 factorial. It is this computed, calculated multiple times. So this way, this recursion becomes inefficient, and this type of recursion is called as naive recursive Fibonacci, because it recalculates the same values multiple times. Are you getting it? Because it calculates the same value multiple times, and if we check its time complexity na, it turns out to be of the order of 2 power n, means it is an exponential time, right? Because at every level you are dividing, then further dividing, then further dividing, and so on. So it is an exponential representation. It is not like binary search you are dividing, then it becomes logarithmic. When you are not this is neglecting the other half of the problem, then it becomes the exponentiation, because at every level it has got multiple branches, and you are solving those sub problems repeatedly, again and again you are solving the same problem. So with that it becomes inefficient. So we say that naive recursive Fibonacci is inefficient. Hope it is clear. Yes or no? Let me clear the drawings. So here we don't perform this na, in order to calculate this recursive function, we don't perform any kind of optimization, because it is calculating same value again and again multiple times. It is doing the repeated work, and with because of that the complexity is exponential, 2 power n. Now what is the remedy for this? Yeah, how to overcome this now? Can anyone tell me what is the how to overcome this? Calculate any number only once. How do we calculate any number only once? What is the method for that? Good, you are saying it right. Calculate. We don't perform any kind of repeated calculation. So what is, how to do that? How do we do that? Actually, we apply optimization techniques. You know, any optimization technique means anything that involves repeated calculation. We have to optimize that. Means that should remove the redundant computation. What are the redundant computation? Means repeated calculations, we have to remove that. And if you remember dynamic programming, in the dynamic programming, if you remember when we discussed the design strategy, it involves the concept of memorization. If you remember, I have discussed, I remember that na chat as well. I told you that we call that as memory stack at that time. Whatever value we are calculating, we used to store that in the memory. And whenever we have to recalculate it, instead of recalculating, we simply refer to the memory location. Right? So all the sub problems, the solution of all the sub problems, once they are solved, their solution is stored in a memory stack, or I can say memory. And whenever there arises a need to recalculate it, we don't recalculate actually, we simply go to the memory location, get the value and do it. So that is actually, we call that as memorization, and the concept is dynamic programming. Actually, that is top-down dynamic programming. Right? Store the result of sub problems when you are computing them at the very first time. Once they are solved, reuse them. No need to solve them again. Right? And here what could be the complexity? It is simply order of n. Hope it is clear. See, you can have top-down dynamic programming as well as bottom-up dynamic programming. Means top-down means we like suppose 6 factorial. You compute 5 into 4, then 5 factorial is computed, right? Then 4 factorial. Again, for 5 factorial is 4 into 3 factorial. Now you don't need to compute the 3 factorial as again. It is like, for example, it is 5 factorial, right? Now 5 factorial is equal to what? It is 4 factorial into 3 factorial. Now this 4 factorial we computed. Store somewhere in the memory, in the computer. Use optimization technique, whatever is the value. Then this 4 factorial is 3 into 2 factorial. Then 3 factorial already calculated. It is 2 into 1 factorial. Right? 3 factorial, 4 factorial is already there some value. 3 factorial is already like some value, or it is Fibonacci, whatever. So here I don't need now to calculate it again. Simply use the value. It is 2, 1. Here also it is 1 factorial into 0 factorial, or simply 1 factorial. Here also. So you don't have to recalculate these values again and again. Once calculated, store in the memory, reuse them. So this is how to. And in bottom up dynamic programming, we actually solve the use cases, these base cases, whatever at the root level. Then we go up. When while you go up, no need to calculate these values again and again. Just refer to the memory, use them, and that is it. So this is how do we perform this top-down dynamic programming and bottom-up dynamic programming, and it is an efficient way of calculating the Fibonacci series, right? So you now know neo recursive and this using dynamic programming recursion. Hope it is clear now. Yes or no, please. Just a thumbs up, just yes or no if you are not getting. Okay, is it fine? Type your message whether you got it or not. So with this, recursion is completed. And there are so many problems that I already named few of the problems that we can solve with the help of recursion, be it factorial, be it Fibonacci, be it Sudoku problem. We can also use this recursion in the backtracking as well. There are so many dynamic programming problems that we can solve with the help of recursion and so on. Okay, fine. Now we'll go to the next part of the topics. Here I have already calculated it is exponential when we have naive recursive Fibonacci. And in the other way, while using the memorization, it is only n. Okay, now we have linked list. What is a linked list now? Also important topic in data structures. What is the linked list? We'll define the linked list, then we'll go for a break. After that, we'll complete its operations. Okay, what is the linked list? Whatever you know, type in the chat box within few seconds only. Data stored in nodes. Go date contain nodes and next link. Great. Nodes have previous and next address. Fine. Very nice. So it means only these few are attentive in the class. Others might be here and there using mobile phones, playing games and other things, I guess. Okay, let me define it. See, simply, if you remember, we have discussed the data structures. Data structures we have categorized in primitive, non-primitive. Then we have further categorized the data structures in linear and non-linear data structures. And when we discuss linear data structures, we define trees, we define stacks, queues, and linked lists, right? So linked list is actually a linear data structure. And these were the data elements, like in case of arrays now, where we store the elements in contiguous memory locations. But in linked list, it is not the case. The elements are not stored in contiguous memory locations like in arrays. Instead, each element, and each element in case of linked list, it is called a node. It contains a data part and a reference link part to the next node. Whatever the elements or nodes are in the sequence, it actually contains two parts. One is data part, another one is link part. And this link is simply referencing to the next node in the sequence. If we check over here, if we see over here, see, it is simple. These are all nodes, or I can say the data elements. And each data element is doing what? It is containing two parts. One is the data part and another one is the, we call it as the reference part or link part. Data is simply data, and this reference part is simply a link which is pointing to the next node. So this is actually linked list. See, it is a kind of a list, but linked. Remember it. List means, what is list? Set of elements, I can say. And these elements are linked, means first with second, second with third, and so on. So it is actually linked list, a list containing some links where the nodes, where the elements are linked with each other. So here, how they are linked? It is containing two parts, data part and link part. Data is simply data and link is simply the link to which it is referencing to. Right? I will give the example also in the next slide, I guess. So one more thing, for a linked list, it has got two important these parameters, or I can say pointers. One is head and another one is tail. So when it is null, we say it is the end of the list, and head is simply starting pointer. It is pointing to the first element of the linked list, or I can say the first node. And there are mainly three types of linked lists. That is singly linked list, we have got doubly linked list, and we have got circular linked list. And now what is singly linked list? Where each node points only to the next node. It is single, means whatever you have, there are only two parts of the node, data part and link part, and each node is pointing only to the next node. There is no kind of a backlink or something like that. So every node is pointing to the one node only. So there is no backlink kind of a thing. That is singly linked list. Only one link, singly link. There is only one reference link. Right? Then doubly linked list. Doubly linked list means, but each node points to both previous as well as the next node. For example, if it is like this, no. Let me 1, 2, 3. See, till now we have only two parts of the node or two parts of the element. Here it has got three parts. Doubly link means it has got two links, back link as well as the previous this front link. So this node is linking, pointing to this. Right? This is data part, it is pointing to back and forth. So there are actually two links. It is both pointing forward as well as backward. So this is doubly linked list. Each node points to both next as well as the previous node. Then we have got circular linked list. Circular linked list is simply means where the last node, like suppose if it is the last node, it is pointing to the, I will not do like this. See, simply if it is the first node and it is the last node, it is link is pointing to its head. So it is connected, you can say, in a kind of a circle. So that is the circular. We will do the operations of all these linked lists. So at that time it will become whole clear. So simply we have got singly linked list where only one link is there, means points only to the next node. Doubly linked list we have got both previous as well as the next node, and in circular last node points to the first node. It is simply it is link is containing the address of the first node. So this is circular linked list. Okay, I guess it is clear. Is it fine? Right here also I have written singly linked list is a linear data structure where each element, or I can say a node, contains data and reference link to the next node. Simple. You have got a linked list like in this case now. In the previous example if we see. So this is it. So this is the singly linked list. Best example. Singly linked list. Right? Now how do we create it actually? Okay, I guess we'll go for a 10-minute break, then we'll explain it. Is it fine? Shall we go for a 10-minute break? Then we'll complete the operations of the linked list. Insertion at the beginning, middle, at last, similarly deletion, etc. And we will check where we will reach. Okay, let us go for a break. The break is, I guess, what is the time? It is 23. So it will be, we will be back at, because if I will complete it now, it will take 10-20 minutes. So then there will be no fun of taking the break. That is why we will be back at 20:13. Okay. Till then, a cup of coffee or tea or some, hydrate yourself. Then we'll continue. Okay, bye. Okay, welcome back. Hope I am audible. Okay, now let me first give the explanation of this, because once we will know this conceptually as well as programmatically, you will be able to understand the linked lists very well. We will try to cover this. Fine, and make sure you have a concept of linked list that we did. Simply like other data structures, this linked list is also a kya? Data structure, linear data structure. Like in arrays, you have elements. Here also we have got elements, but the elements in linked list are called as nodes. Fine. The elements in linked list are called as nodes. Remember it. And here in linked list, the elements or the nodes, they are containing two parts, data part and link part, or I can say data part and reference part, right? Or next part. So we'll be explaining this, what this code is actually. Fine. Okay, let me explain it. See, I can tell you simply we are writing a class node. So we are creating a node, isn't it? And you know what class is? Class is simply what? It is a blueprint, right? In Java, class is simply a blueprint of creating objects. Fine. And each object of this type, node, it will represent one element, or I can say one node in a linked list. By this first line, what do we mean? We simply mean we are creating a node. Actually, it is a class. Class is simply a blueprint of creating what? Of creating objects. And we know each object of type node, it will represent one element, or I can say one node in a linked list. Fine. So with this, then we have, if it is a node, it is containing two parts. So we have to define, we have to declare that, because we have to create a node. So this is the data part and this is the link part. So what is the data that we are going to place over here? So that is simply integer data. We are declaring that of type int. Right. So we are simply writing in data, it means data stored in the node. Or I can say this is an instance variable named data. It can store what? It can store the value or the content that we want to keep in the node. And you know, type is int, means it will store integer values 1, 2, 3, 4, 10, 50, 100, etc. etc. Now the next part of it is node next. What does this mean? See, once you will understand this concept, now it becomes easy. What is node next now? This is simply a reference, this node next, or I can say a pointer to the next node. Means if I have a next node over here, here also I have got data part and link part. This next node, it is simply a reference, node next, or a pointer to this node. This is node 1. If it is node 2, this node next, it is simply a link to the next node. And its type is node. See, it is node next. It is like here it was int data. Here it is node next. So its type was int. Its type is node, right? Which means whenever we say the type is node, it simply means it is pointing to the another object of the same class. Fine. So whenever we are just saying it is a type of node, node and next, node is simply a type which points to another object of the same class. And next is another, like suppose here it was int data. Here it is next. Next is simply this na node next is simply a variable which is pointing to the or a pointer which is pointing to the another object of the same class. So with this we are creating a link part of the link link list by connecting it to the another node. So simply what we are doing with this node next is, with this node next, what we are doing, we are simply creating a link part of this linked list by connecting it to the other part, another node. So this way I can say this, that I have created this by these three lines. What I did, I have created a class, or I can say blueprint. In that class I have created a data part and the next part, and this data is simply data part of this, and this next is simply a reference part, or I can say a link. So with this I am creating a link and this node. So a node is created, simple, by 2-3 statements only. Simply declare a class node, give data to it in data, another part of the node, that is the reference part, simply it is node of type node and the variable next. So that is it. Now I have another function over here, this public node in data. What is this? It is actually a constructor, right? It is a constructor method for this node class. The node class, let me clear the drawing. This is a node class and this is a constructor of this node class, isn't it? Because if you remember the opus concept, the name of the constructor should be same as the name of the class. So here also it is node, here also it is node, and it is called automatically. Whenever we create a new object, this constructor, this node is called automatically, and here it is taking an argument, that is data. Fine. Then we have this statement, this dot data and this dot next. Can anyone tell me what is this actually? This dot data and this dot next. Yes, what is this dot and this dot data and this dot next? Yes, it contains the address of the next node. Fine. Anything else? This dot data and this dot next. Two statements are there. Yeah, what is this representing actually? So if you know, we have created an instance variable over here in data. So this dot data is simply referencing to this new node, this instance variable data to the of the current object. So it simply refers to the instance variable data. This dot data is simply referencing to the instance variable this data, right? And this right data, what is this data on the right side? It is actually the parameter that is passed to this constructor. In its public node in data, whatever the parameter is in the constructor, this right side part is giving as a parameter to this constructor. Simple. Then this dot next is what? It is simply setting the next part of the node that you have created to null. Means if it is like this, here goes the data part, this dot data, right? D, and here goes the null. It is simply this dot null. It means when I say it is null, so what does it mean? It means that this node does not point to another node. Whenever I am writing this dot next is equal to null, so it means it is not pointing to the next node. So it is the, I can say it is the end of the linked list. Fine. Got it? So usually when we do, initially we do like this, means this dot next is null. So whenever whenever a new node is created, we will be linked it later if needed. So then it is finally the end of constructor and end of the class. Hope it is clear. Yes or no? Yes or no? Okay, good. See, it is now simple. If I will give an analogy, let me give an example. For example, I can write like, you can think of as a box or more, yeah. Let us take a scenario. You might have seen that not this toy train having multiple those boxes, coaches I can say, and or even a normal train as well. Let it be the train that we have. We have got multiple coaches in the train, isn't it? And that coach is carrying what? The coach is carrying passengers. We can say data, right? Passengers or data. And these coaches are linked to one another. Means there is a connector between every coach. First we have DMU engine, right? That is pulling the whole train. Means that is connected to the first coach. First coach has a link. That link is connected to second coach. Similarly, second coach has a link. This next part, node dot next. That is linked to another part until the end of the train. So this train is simply a node, right? It is containing passengers and it has got a link part that is pulling, that is connected to the next coach. Similarly, that coach has got data passengers that is connected to the another coach, though it is kind of a linked list. So this coach is actually a node in a linked list. Hope it is clear. I guess the best analogy of linked lists, right? Is it clear? Yes or no? So this is actually how do we create a node in a linked list. Simple. Create a class, blueprint of the class, assign data, assign node, then create a constructor, give data to it, assign that to null, means end of the list. If you want add the nodes, we can add them later. Okay. So let us now move to other part of the linked list. Let us go to the operations of the link. What are the several operations that we carry over the linked list? Simple. See, I hope you will find this. Simple. Data structure node in data node dot next. That we did. It is same. We are creating a node, data part, link part, then singly linked list node head. So it is like a previous part that we did programmatically. So you won't be now. If I will ask you to create a linked list, it is simple now. So basic is create a class node. In that class, we have two parts: data part, in data, and next part. No of type node next. Then simply create a constructor of the same type, like suppose node. Then in that pass data, whatever you want. Then this dot data, this dot next, and that's it. So you are creating a linked list. So easy way to create a linked list. As I have seen, because most of the students, almost more than half in the class, once we start linked list, they hands up to the programming, because they think that it is kind of a rocket science. Whenever they say, like, if we would talk of C programming, those arrows, etc., that it is like this dot, where we have that pointer kind of things in C. Similarly in Python. So actually, it is more easy than that kind of a programming. So don't get frightened about it. It is very easy. That is why I give some more extra time on this construction part only, linked list node construction. Because once you pick up this in the mind, it would be easy to do the things later on. So try to create this part, node part, data part, and node itself. Means in node we have two parts, data part and link part. So try to create it. Later things will be easy. How to create, how to insert, how to delete, etc. It is all easy. There is no like any kind of this difficulty. You won't find any kind of difficulty later in it. Right. Okay. So if we see the operations, we have seen these operation arrays as well. Here also we'll see these operations. The very basic operation is the insertion operation. Right? Insertion is simply whenever we have to add a new node to the linked list. Right? So what we will do? Insert at beginning means whenever we want to insert the node at the beginning of the linked list. If you have got this linked list, you want to insert a node means you have this linked list till now. You want to insert a node to this linked list, but at the beginning means at the start of the node. Right? So input would be integer data to be inserted means we want to insert some data into the linked list. Right? Then output would be, what would be the output? Output would be the linked list with this inserted node. Right? Now how do we insert? Simply we'll create a new node. How do we create a new node? The step that I already told you, like this, or in the previous example. Then set new node dot next means whatever node you have. If you remember here, let me go to the previous slide. Here, this way you have to create a node, right? But this dot next you don't have to write null. You have to write overhead. Means now you are referencing this node to the first node. Means if this was the first node and you want to create a new node in front, so this next would be its head. So it will be referencing to the head. So that is why here if we check, we are saying that the set head is equivalent to new node. Means you are simply referencing the head by the new node that you have created. Right? So this is how do we insert a node at the beginning. If I again explain it simple, see, this was the linked list. This was the first node before insertion. Now I have created a new node like this. And when I create a new node, I give a data part and I give a link part. And while creating, I usually give this node dot next is equal to null. But instead of node dot next, instead of giving it to null, so what I will write? I will write head in it. Means the head part, which was referencing to the first node, it will now refer to the new node. So this will become the first node of the linked list. Right? It is simple. Okay, so this was insertion at the beginning. Now let us see insertion at the end. It is easy. Insertion at the end is easy. Simply here also we have integer to be inserted, and in output list with new node at the end, it would be the output. What are the steps? It is same step. Create a new node with data. Fine, I have created a new node. Now I have to check if head is equal to null. So what does this mean if head is equal to none? Can anyone tell me? What does this mean? Head is null. If head is null. Yes. Yeah, linked list is empty. Good. So if linked list is empty, it means that it would be the last as well as the first node itself, the node that I have created. So simply set head is equivalent to new node, the new node that I am creating. And you know now how to create a new node. So simply for that new node, I will be setting head is equal to new node. If it is the first node itself, means if the list was previously empty. Now if that is not the case, so at that time what I will do? I will simply set current is equivalent to head. Means this, I will create a current head and I will give it to current. Then I will traverse the linked list and I will check while current dot next is not equal to null. Can anyone explain what does this mean while current dot next is not equal to null? It means when I will set current this, is it is next null? No. 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 Yes. So when I traverse like this while current dot next is not equal to null, it means we are searching for the last node. So whenever I found that current dot next is null, it means it is the last node of the linked list. Because whenever we have to insert a node at the last. So for that purpose, I have to check current dot next is null. If it is not null, then I will say it is an intermediate node. Right? So once I found that current dot next is null, simply I will set this current is equivalent to current dot next. So whatever is the next, I will set that to current dot next. So with this, what I am doing, I am simply like removing this null from this node and I am giving it to the node that I have created. So current dot next, it will go to the current, means this current dot next would be like this, it will go to this next node. And the next of this inserted node, it would be then null, means the new node would be simply the current dot next. Right? I hope the algorithm is clear. You want me to repeat it? Simple. There are two things to check. The very basic thing is whether the list is empty. For that, what I am checking, if head is null. So if head is not null, it means there are some nodes in the list. And the second condition is that I have to check for the last node. For that, what I will do, I will set head is equivalent to current, means this head I will set it to current. So for that, I will look for the current dot head. If this current dot next, if current dot next is null, I will designate that node as the last node. And for that current dot next, I will give that to current, and I will simply replace the current node with the new node. So with this, I am inserting the node at the last. Hope this is clear. Yes or no? Then we'll write the program for it. Is it clear? Is it fine? Yes or no? Okay. Then we have another thing, that is insert after, means at some place. So we have a node, previous node. We have some integer data. Right? Then what would be the output? It would be simply a new linked list. And we have inserted a node after some node and before some given node. So here I have some previous node is null. If previous node is null, it means previous node cannot be null, simply because I am inserting the node in between. So if previous node dot this previous node is null, it means simply it is the last. Then again I will create a new node the way that I have created. Simply then see, set new node dot next is equivalent to simple. The link part of this will act as a link to the new node, and the link of the new node will act as a link of the next node. Simply, new node will simply refer to next, and this previous node will simply refer to the next node, the new node that we have created. Simple. Cut this reference, give this link to the new node, and this node will ask for the link, give the link of the new node to it. So that is how do we insert a node after a given node in a linked list. So this way we are actually doing what? We are inserting the nodes in a linked list. Right? Okay, no problem. Once we end all the sessions, we'll try to share this content with you. Hope it is clear. Yes or no? Then we'll do the programming part. Okay, if it is clear, just give a thumbs up or yes or no, whatever you feel. Then we'll move to the next part. You also make use of the hands. Try to type, ask a question, etc., etc. Don't be idle. See, actually, the class should be, as you know, you are from computer science, right? You are tech people. So the communication should be, yes, it should be simplex, duplex, or full duplex. What the class should be? It should be full duplex, obviously. Unless and until the class is not full duplex, it is a kind of that, I can say, kind of that YouTube video, checking a YouTube video or going to a theater, watching a movie. It should not be like that way, because whenever we are in a class, we have to be interactive. Ask questions, give answers, ask doubts. So this way things are becoming more clear. So always the class should be full duplex, right? We should be communicating in full duplex mode. But most of the times it is, but it is simplex, only one way. You are not asking anything, you are not giving responses. So that's why I feel it is most of the times it is simplex. So try to make it full duplex. Okay, fine. So let us go to the programming part. And I hope it is clear to you, the algorithms. Because once you have the algorithms are clear, programming part is simple. It is simply then how good you are in the programming. Logically, if you are sound, the programming part you can learn. Unless and until you are not logically sound, if you know the programming, then it is of no use. If you don't know how to create a new node, how to insert the node in the beginning, how to insert the node at the last, how to insert a node after a previous node. So logically, if you are not getting it, the link part, data part at the last, how to check the node is last, how to check the node, this list is empty. So when you have all these things in mind now, and the image of these things is clear. So it is simply what? Then there is no fun of doing the programming. You can relate this to the train problem as well. You have to insert a node at the last. You have to insert a coach at the last. What you will do? Means at the last coach, the coach which was last till now, it was referring to null, means end. So what you will do? You will simply move that null part, insert a new coach, and the new coach will contain the null itself. If you have to insert at the beginning, what you will do? You will simply move demo. Demo is like kind of a DMU, the engine, I can say. It is kind of a head. So what you will do? You will replace the head. Firstly, head was simply linking to the first part of the node. Now what will you do? You will simply connect this head to the new node, and you will give the link part of new node as a link to the previously existing first node. Right? And when you are inserting a node after some a coach after some few coach, like suppose you are you have to insert an AC coach after third AC, first AC, second AC after third AC. What you will do? You will first remove the link of the third AC which it was referring linking to. So you will connect that link to the new coach, this second AC coach, and the second AC link will connect to the previously connected coach of that was connected to the third AC. So it is simple. So this way you can insert, delete this insert nodes at different locations. Okay, so this is the programming part of it. See here. Simple. I am creating a class of singly linked list. Then what I am doing? I am creating a node, private node, head. Simply I am creating head, simple. Then this dot head is null. Simple. The way that I created a node. This is it. Node part and null part. Head and then insert at the beginning. So for that, what I am doing? I am simply creating a new node of type node and I am giving data to it. Then new node dot next is equivalent to head. The head that I have created means I am simply wrapping connecting this head to the new node. So it means if it was head, I am connecting it to the new node that I have created. Right? I have wrapped it. So this is the head now becomes the new node. So this is simple. Similarly, if you have to insert at the end, so for that, what I am checking? I have to check some conditions. If head is equivalent to null, head is equal to new node and return. Means if the list is empty, else head will go to the current node. Then I have to check the condition. While current is not equal to null, so I will start check for the last node. Whenever this current will check that it is next is null, so it means that is the last node. So for that, if that I found, I will simply write current का जो next है, that will simply go to the current and I will update the current node, that is new node. So this way we are inserting at the end. Then in between, after a specific node, that I have to specify if previous node is equal to null, previous node cannot be null. Simple. Because if you have to edit after some node, then return, or simply new node data, it will go to new node, then previous node next, it will go to new node of next, new node will simply become the previous one. So this is how do we do these operations on singly linked list. Hope it is clear. Yes. Is it fine? Yes or no? Yes. Please tell me. If it is okay, you can tell. If not, okay. I got some questions. Yeah, insertion at a specific node. See, simple. Here, okay. Just a minute, I will create a linked list. Okay. So consider this as a linked list, right? Now we want to insert a new node, like suppose at here, at a specific location. So this is head, it is pointing to the first node, and it is the last node, it is pointing to, like suppose, null. Now we want to insert this node after this previous node. This node. After this, we want to insert a new node. So what we will do? We'll firstly check if head is null. Means if this head is null. What does that mean? That means the list is empty. So then we will return. Set temp is equivalent to head. Then we'll set if position is equivalent to 0, set head is equivalent to temp dot next and return. Means it will simply show this if your position is at this place, 0th place. Then we will simply set kya? It means when we are inserting after that, we'll simply write temp dot next is equivalent to head. Then the new node which we are going to insert, it will simply be referred to here. So the node will become a new node itself. Now what if we have to insert it between? Means here. Right, let me draw this annotation over here. See here. Now I want to insert over here. This is actually delete that I am showing you. Okay, so we are actually checking for the previous node. Previous node cannot be null. Now we have to create a new node. Now like suppose I have created this node as new node. The way we are creating. For this node, see, I have to set new node of next. Previous node of next. This is the previous node of next. This part. Because previous node was linking here. So this is previous node next. So it is referring to the new node, not the new node, the node that is to the next of the previous node. Now I want this link to get disconnected and I want this link to be connected over here. So for that I am simply giving this previous node of next to the new node, means this previous node link, it is simply link of previous node. Instead of giving it to the node that was after it, give it to the new node. And this new node link, give it as a previous node का जो next था. Again I am repeating it, simple. See, this is previous node of next, because this was previous node and this is previous node of next. This is new node and this is previous node. This is previous node of next, isn't it? And I just want give this previous node of next to now what? I want this to be given to the new node of next, right? And this link, new node, to what I will give it? I will give it to the previous node of next. So this is previous node of next, this is new node, and this is new node of next. This one. So I am simply changing the references of these links. So with this, we are simply creating a new node, right? Hope it is clear. Yes. If you are getting it, Please tell me. If you are clear, you can ask. Yes, you want me? Okay, there is one more question. Why the head node is private? See, you might be knowing, I guess we call that as access specifier, right? We have got public, private, and I guess public, private, and third one is I don't remember exactly. Public, private, and that is not that access. Public has got access. It is this na member functions can be accessed anywhere. For private, we have limited, and for can anyone remind me the third one? Protected. Yes, kind of constructors we call them as. So when we write now this public class singly linked list, let us go to that slide. This public class singly linked list. What does this mean? This simply declares a public class with this name, and we will be implementing the linked list operations on this. Then I have written private node head. So it simply means it will declare a private instance. Means a private instance variable head will be created of type node. And this will always point to the first node, because whenever we are saying head, so it will always point to the first node. And this private access modifier, it will this now with this what we will do by private, it simply ensures this encapsulation, means only class methods can modify it. So that's why I have chosen it as private. So private is actually access modifier, means only this class methods they can access it, right? If we explain the code further, then we have public singly linked list this dot head. So what does this mean, this dot head? This constructor method, it will get called when a new linked list is created. So when I said this dot head is equivalent to null, it means the head pointer is pointing to null, means the list starts empty, means there is nothing in the list. And this keyword, like you have that arrow key in this na C, this key also this keyword, it refers to the current instance of the class. So this dot head is equal to null means it will initialize it to null, this now head pointer to null, and simply it will designate that the list status empty. Then after that what we'll do, we are simply inserting at the beginning. So if we break down this program line by line, so the very first line public int this line, where is the editor, this line public int insert data at beginning in data. So public method does not return anything, it is simply void, right? This it takes integer as data as a parameter. So after that we have node, new node is equivalent to new node data. What it will do, it will simply create a new node with the given data. So we have got data field and next field in the node that we already discussed. Two fields are there, data part and next part, or I can say this reference part. Then after that we have new node dot next is equivalent to head. So it will set the new node's next pointer, means the node that we are creating, like this. This is the node that we are creating. it will set its pointer to whatever head is currently pointing. For example, if head was currently pointing to, like suppose this node, so now the new node will be pointing to where this head was actually currently pointing. So this link will get removed and this link will be created. So with this way, this new node has pointed to the first node of the linked list, the previously first node. So if list is empty, what does this mean? It simply means that this node will point to null. Because if list is empty, so it means what? It means, let me change the color. If list was empty, like suppose this was head. So what does this mean? This means head was pointing to null, isn't it? So when I say set this new node dot next is equal unto head, so I will set the next pointers, next pointer to point to the node where head was pointing. Head was pointing to null. So this node that I am creating, it will point now to null. So it means it will become the first and the only node of the linked list. Right? So now if it has elements, this linked list. So what does this mean? This makes the new node point to the current first node. So if it was the first node, right, it was head. So head was pointing here. I have created a new node. Now I have created this node where the head was pointing. I am removing this link. So I will simply point to this new node. So then head is equivalent to new node. After that, I have this head is equivalent to new node. So what does this mean? Head is equal to new node. So this simply means that it will update the head pointer. Initially head was there. I have removed it. Now head will point to here. So with this way, this node has been inserted. And it will make this current new node as the first node of the linked list. Got it or not? Yes or no? Use of this key. Which key? Yeah, this is actually a keyword in Java that refers to the current instance of the class. So this dot head, when you write, it simply means we are initializing the head pointer to null. It is a keyword in Java, this. So like you have, I guess, in C, if you have remembered, there is an arrow operator, this. Isn't it? So here in Java, this is a keyword that is referring to the current instance of the class. So this dot head, when you have this dot head, so what does that this dot head mean? When I write this dot head is equal to null, what does it mean? It simply initializes the head pointer to null. So it means that the list is empty. Means there is only one head and it is simply referring to null. So the linked list is empty. There is nothing in the list. Hope it is clear. Yes or no? Then you have insert at the end that we discussed, insert at a specific node. If you want me to explain these things as well, I will explain. Or if you have any doubts, you can ask. Yes, any questions? Yeah, can you tell me what is the complexity of insertion in this linked list? Can you tell me the complexity? Again, see, complexity now actually depends upon what? on the position where actually the insertion occurs. We have seen three cases: insertion at the beginning, insertion at the end, or insertion at middle, or at a particular position, right? When we say insertion at the beginning, so the time complexity is what? Can you write what is the time complexity? It is simply order of 1, constant time, isn't it? Simply what way you have to create a new node, point to next, update head. That is it. So it would be what? Order of 1. There won't be any kind of a traversal. No traversal is required. So it will take the same time regardless of the list size. So the complexity would be order of 1. When we have to insert at the beginning, right? What if what is the complexity when we insert at the end? Insert at the end. So it would be order of n. How? Because at that time we have to traverse the entire list. Here you have to traverse the entire list. You have to check this. Head is equivalent to null. To which node's head, to which node is pointing to null. When you are setting the current, if current is equivalent to head. So here you are actually checking for the last node. So you are traversing the whole list. So for that purpose, we are just saying the complexity is order of n. Right? Okay, what is the insertion at, I can say, after a given node? So it depends. It can be order of 1, it can be order of n. Means if you have a predefined reference, means if you have already some node reference, so then it can be order of 1. So if you have to search for the reference node, means after which node you want to insert the node, then it is order of n. So this way we have completed the insertion operation in linked list. And for all the cases, the space complexity is 1. Hope it is clear. If you have any questions, you can ask. Yes. If you have got any questions regarding the linked list, please ask. Okay, any questions? I hope it is clear. The insertion, the linked list and the recursion. Insertion at the beginning, insertion in middle, insertion at the end. Okay, thank you so much for joining the session. Good night, take care, bye-bye.
Yeah, thank you, sir. Yeah, students will meet again by tomorrow at 8 p.m. Sorry, 7 p.m. Thank you all for joining. Good night.